Welcome friends, Igor is here, and in this video we will learn how to describe spans in the most efficient way. In this lesson we will follow a systematic procedure for casting out vectors which are not necessary to describe the span, and we will learn that the most efficient way to describe a span is to use a linearly independent set. Let's get started. Let's learn a systematic way for discarding vectors that are not necessary to describe spans. And I will illustrate this procedure using a specific example. We are given a set of 7 vectors from C4, and we construct W, the span of this set of vectors. So W is an infinite set which contains all possible combinations of the given 7 vectors. The set T contains 7 vectors of size 4, so there are more vectors than this size, and we know this means the set T is linearly dependent. This is an indication that we do not need all vectors from the set T to describe the same span W. Some vectors are not necessary and we can discard them. Let's figure out which vectors we can discard and how we know that these are the vectors that we can discard. I'm going to construct a matrix A by using vectors from the given set T as columns of this matrix. The homogeneous linear system with A as the coefficient matrix has infinitely many solutions because there are more variables than equations. There are 7 variables, that's the number of columns in the matrix A, and there are 4 equations, that's the number of rows in the coefficient matrix A. In turn, it means we can construct non-trivial relations of linear dependence on the columns of the matrix, and the columns of the matrix are precisely the vectors in the original set T. To construct non-trivial relations of linear dependence, we need, of course, solutions to the homogeneous linear system. And to solve the linear system, we find the reduced row echelon form of the coefficient matrix A. From this reduced row echelon form, we see that there are 3 dependent variables and there are 4 free variables. The dependent variables correspond to pivot columns in the reduced coefficient matrix. These are columns 1, 3, and 4, and free variables correspond to non-pivot columns. These are columns 2, 5, 6, and 7. Any of the infinitely many solutions of the homogeneous linear system is going to produce a relation of linear dependence on the columns of the coefficient matrix. But we will construct some specific solutions in a very careful and systematic fashion. Then we will use these solutions to eliminate vectors from the description of the span. Let's get to this. Here is a quick preview how we are going to accomplish this. What we are going to do is we are going to assign a value of 1 to one of the free variables and the value of 0 to all the other free variables. There are 4 free variables, so we will go through this procedure 4 times. First, we are going to assign a value of 1 to the first free variable, x2, and 0 values to the other free variables, x5, x6, x7. By fixing values of all free variables, we construct one particular solution of the homogeneous linear system. And in this solution vector, I emphasized the values which correspond to free variables to make it very clear that one free variable is equal to 1, the other free variables are equal to 0. We know that solutions to linear systems result in linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. We have a coefficient matrix A, vector of constants 0, and this means if we use components of this solution vector as scalars, then the linear combination with these scalars of the columns of the coefficient matrix A must be equal to the 0 vector. In turn, this gives us a non-trivial relation of linear dependence on the columns of the matrix A. Because we assigned a value of 1 to the free variable x2, it means that the second column vector appears in this linear combination with a non-zero scalar. This means we can solve this equation for the vector a2. In one of the previous videos, we discussed that this means we do not need the vector a2 to describe the same span W. Therefore, we can discard this vector and still obtain the same span. Let's repeat this procedure again, but now I'm going to assign a value of 1 to the next free variable, x5. The other free variables get assigned 0 values. This results in another non-trivial solution of the homogeneous linear system, and we use this solution to construct a non-trivial relation of linear dependence on the columns of the coefficient matrix. Because I assigned a non-zero value to the free variable x5, it guarantees that the column vector a5 comes with a non-zero scalar, and therefore we can solve this equation for the vector a5. Also, note one important thing. We already discarded the vector a2, and because I assigned a zero value to the free variable x2, this vector will not explicitly appear in the expression of the vector a5 in terms of the other vectors in the set. We already know that this expression for the vector a5 in terms of the other vectors means that we do not need the vector a5 to describe the same span. Therefore, we discard this vector. We continue this procedure for the third round, and now it is the turn of the third free variable x6 be assigned a value of 1. All other free variables get assigned values of 0. We get another non-trivial solution to the homogeneous linear system, which results in yet another relation of linear dependence on the columns of the matrix A. This time, it is the vector a6 that is guaranteed a non-zero scalar, and therefore we can solve this equation for the vector a6. Also note that we already discarded vectors a2 and a5, and I assigned 0 values to the free variables x2, x5. Therefore, these vectors do not explicitly appear in this linear combination. As before, this means we can discard the vector a6 and still obtain the same span. In round 4, we assign the last free variable x7 the value of 1 and zeros to all the other free variables. And again, we have a particular solution to the homogeneous linear system, which we use to construct a relation of linear dependence. In this relation, it is the vector a7 that is guaranteed a non-zero scalar, and we can solve this equation for the vector a7. Also note, the vectors we already discarded, a2, a5, a6, come with 0 scalars in this expression, and therefore they do not explicitly appear in the expression for a7 in terms of the remaining vectors. As before, this tells you that you can discard the vector a7 from the list of vectors and still obtain the same span. Now, we cannot continue this procedure because we exhausted all free variables. Moreover, the set of remaining 3 vectors is in fact a linearly independent set. Please check that indeed the first, third, and fourth vectors from the original set T form a linearly independent set. This means that no further reduction is possible. We cannot discard any more vectors. Why this is the case, we will understand a little later. This was a long computation, so let's recap what we achieved. We started with a set of 7 vectors of size 4. We used these column vectors to construct a matrix A. Then we looked at solutions of the homogeneous linear system with this matrix A as the coefficient matrix. We discovered that there are 3 dependent variables and there are 4 free variables. The dependent variables are x1, x3, x4, and the free variables are x2, x5, x6, and x7. Then we were able to show that the span of the set of all 7 vectors in fact can be described as a span of the first, third, and fourth vector only. In the process of discarding vectors, we used one free variable at a time to eliminate the corresponding vector, the column that corresponds to that free variable. So in effect, we eliminated all the columns that corresponded to free variables. These are the non-pivot columns in the reduced form of the matrix A, and we kept those columns that correspond to dependent variables, those columns that correspond to pivot columns in the reduced matrix. Moreover, no further reduction is possible because columns corresponding to the pivot columns in the reduced matrix are in fact linearly independent, as I asked you to check. Let's formalize our findings in the following general statement. Suppose we have a set of n column vectors. We construct the span W of this set of vectors, and we construct a matrix A using these vectors as columns. We look at the reduced row echelon form of this matrix, and we record the indices of the pivot columns in the reduced matrix. Then, the columns of the non-reduced matrix of the matrix A, which are the vectors in the original set, which correspond to pivot columns in the reduced matrix, form a linearly independent set. Moreover, these vectors still span the same span as the original set of vectors. Here's the essence of this result. Here's what this result tells us. We can start with any set of column vectors. We can then construct the span of this set. But this might not be the most efficient way to describe this span because we might be able to get rid of some of the vectors. And what this result tells us is this. Starting with an arbitrary set of vectors which we use to construct a span, we can reduce this set of vectors down to a linearly independent set. And this linearly independent set still produces the same span as the original, possibly larger set of vectors. So in essence, linearly independent sets are the most efficient ways to describe spans because these sets contain all the essential information. You cannot get rid of any vectors from a linearly independent set. This result also uses a new word, basis. This is not an accident. It is a very definite and specific terminology, and we will understand the meaning of the word basis when we start talking about abstract vector spaces. Here's a quick preview. A basis is a linearly independent set which also spans a given space. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define the operations of matrix addition and scalar matrix multiplication and discover some of their properties. I will see you later.